In this lecture, we're going to talk about nomenclature. Nomenclature is the fancy word for saying how to name a chemical. And now that we've introduced these coordinate covalent complexes or compounds, we need to know how to name them. And this will build on the rules about naming that we've already talked about for ionic and covalent compounds, and it'll kind of bring those two together and add in some new kind of best practices. Not the right word, but it's escaping me right now. But build in some kind of new methods for naming as well. So let's start at the top. The idea here is to name a complex ion that's in a compound, but we are naming the entire coordination compound, which is going to typically include a complex ion plus that counter ion. And together, these make up the coordination compound. And so the easy place to start is to determine the name for the non-complex ion. And so that's going to be your counter ion. If it's a chloride ion, it's just chloride, right? And this is going to follow the rules of ionic naming in that sense, or ionic nomenclature. And then from there, we're going to work on, so that's one. And then going into step two, now we're going to start working on building up that name for the complex ion. And so this is going to be a series of steps where we'll start with determining the Ligands names. And so those are those atoms or molecules that are surrounding and forming the coordinate covalent bond to the metal. So we have two different types. We have neutral ligands and we have anionic ligands. Our neutral ligands are going to be named as followed. And there's just a few examples here. There's more out there that can be looked up, but these are our common ones. We have water molecules that will be named aqua. Carbon monoxide will be carbonyl. Ammonia will be amine, and NO will be nitrosyl. And these are ones that you may choose to memorize or choose to look up as you see fit. As you get used to working with these and you find yourself naming them a lot, you get used to these names. But that takes a fair amount of practice and exposure. And I feel like it comes when you're actually working in a lab that uses these compounds more than anything else. So now if instead you have an anionic ligand, so it has an overall negative charge, then we're going to name that name very similar to the ion name we would do for an ionic compound, but we're going to modify the ending because chemists love to modify the endings of things. So we're going to take the IDE ending on these and replace it with an O. If it has an AT ending on the anion, we're going to replace it with an ATO. And if it has an ITE ending, we're going to replace it with an ITO. So the trick is it's going to have an O at the end. So here's some examples. So something like chloride would become chloro. So we're dropping that entire IDE ending and we're adding that O. So we start with chloride and we're taking that IDE and we're getting rid of it. And then we're adding the O. We're adding the O to it. And so we've basically replaced IDE with O, and we get chloro. Sulfate will become sulfato. Sulfato. This one's hard for me to say. And ite will become ito, so sulfito instead for our naming conventions. And here are some common ligand names that you would use. Their given name as an anion, and then how you would convert that to the name to use for a complex ion. And so as you can see, our simple halogens like bromide and chloride become bromo and chloro. And hydroxide, which is a polyatomic ion, but has that IDE ending, becomes hydroxo. Cyanide becomes cyano. Nitrite becomes nitro. Oxalate becomes oxalato, gelato, I don't know. Anyway, some ones that I wanted to add to this list too, an oxygen bonded to a carbon bonded to a nitrogen that has an overall -1 charge will be cyanato. And then we have thiocyanato as well when there's a sulfur instead of an oxygen. So these are our anion names that you can reference. The ones that are boxed in red have this really interesting thing they can do. They have two different methods of bonding to the actual atom or to the metal atom. So they can be connected. So let's look at the cyanido here. It can be connected through the nitrogen atom, which has lone pairs to donate as a Lewis base, or through the oxygen. In thiocyanado, it's the sulfur or the nitrogen that can donate that electron pair to the metal. And so there's two different ways they can bond. And we'll talk about that more when we talk about isomers. Then we have our neutral molecules here for quick reference. Some ones that I added to this include nitrosyl, which we mentioned on the previous slide, diethylene triamine as a diene. So this is one of our tridentate ligands. We have a few other ones. We have ethylene diamine, which will abbreviate EN in a chemical formula, and it will be a bidentate ligand. And then we have ethylene diamine tetraacetate, which is a mouthful, but that was why we called it EDTA when we referenced it before, and that was our hexadentate ligand. And so some of these names get impressive, and those large naming structures really come out of organic chemistry and are conventions for naming organic compounds. Okay, so moving on, now that we've kind of got the idea of how we name ligands, which is a whole thing, then what we're going to do when we're naming that complex ion is we're going to list the ligands in alphabetical order before we say the metal cation name. So amine would be first, it's got an A, chloro would come next, it's got a C, then nitrosyl would be with an N, so it would be last in some sort of naming structure. We are also going to then indicate the number of each type of ligand as well. And we're going to do that with the language di with a prefix. Di, tri, tetra, penta, hexa. And that can go on hepta, octo, etc. And so the one time that we don't use this, and I wish we just had one method or another, but if the name of the ligand already has one of those prefixes embedded in it at the beginning or in the middle, we aren't going to use it. It would be super confusing. And so we differentiate for things like diethylenamine or ethylene diamine tetraacetate, is that we use bis, tris, or tetrakis to say 2, 3, or 4 of these ligands. And then we'll put the ligand in parentheses as well. So the ligand goes in parentheses, you can see those right here, and we put our prefix that tells us the number of those ligands out in front of the parentheses. So 3 ethylene diamine molecules would be tris ethylene diamine when you write out the name. Now, when you're putting this in alphabetical order, don't include the prefix to indicate the number of the ligand as part of that alphabetical ordering. That's a separate consideration. Okay, now that we've got our ligands sorted, we need to name the metal ion. And if the metal ion forms a complex ion, that's a cation. So in this case, the complex ion itself, the whole thing needs to be a cation, then you can just use its regular name. And you'll still use the parentheses to indicate the oxidation state, because our transition metals can have lots of oxidation states and we need to know. And so we might have like cobalt-3, which I think is now the simplest thing I've told you about naming this, other than your complex ion or your counter ions can just be chloride. But if the complex ion forms an anion, we're going to change it up. We're going to change the ending of it. We'll still include the oxidation state in parentheses, but we're going to drop the ending of the metal and add an ATE ending instead. Now, some metals already like that have a Latin root with that AT ending anyway, so there's that. So let me show you some examples because that helps me. And some of these with the multiple common types have actually a different set as well for the lower of the common oxidation numbers. But let's look at this. So iron will become ferrate, right? And that's coming from ferric and ferrous for iron plus 3 and iron plus 2. If it's iron plus 2, it's ferrum. Lead would become plumbate. I'm sure I'm butchering that. Nickel, nickelate. Palladium will be platinate. Why did I choose the hard ones? So please don't go through and memorize these. Please reference this chart instead and save that brain power for something else. If you get really into transition metal chemistry and research later on in your career, you'll have plenty of time to get to know these names intimately. Okay, so now we have to put this all together. So to put this all together, we're always going to follow some of our basic rules. We put the cation first and the anion second. So that's, key in this. So we always have the cation will always come first, no matter what it is, if it's the complex ion or if it's the counter ion. And we're going to start by putting our ligands first. So we'll go in the order of ligand. We'll use our prefix for the number of them first for our ligands. We'll do our series of ligands in alphabetical order. Then we'll do our metal name and its charge. And that'll make up our complex ion. And then if it's the cation, then we'll follow it with the anion, or if it's the anion, we'll lead with the cation name. And so here is an example to look at. So just working on naming the complex ion, we've got this platinum bonded to some amines or ammoniums and then chlorines. And so I have 2 of these amines and A comes before C. So I'm going to start with diamine, and that's corresponding to this part of our chemical structure. Then I have 4 chlorine, so tetra for 4, chloro. And then I have platinum, and this forms an overall anion complex. So I'm not going to do platinum 2. I'm going to do platinate 2, and that's my oxidation state on the platinum. And now I have my complex ion named. Now, cation first, anion second. So that anion name comes in second, and I'll start with my cation name, which is just potassium. Nice, simple potassium. I don't need to put the number of atoms because I'll be able to figure out the charge for my extremely long name for my complex ion, even if it takes a minute. And I'll be able to figure out how many of those potassiums are really in this complex. So we've got our cation first, followed by our anion. And we get the ever so long name, potassium diamine tetrachloroplatinate 2. It's a mouthful. Inorganic chemists who study transition metals and coordination compounds tend to not write out full names. They tend to just write out chemical formulas instead for this reason. So in here, I've got another couple examples for nomenclature. So walking through one here where we're going to have our complex ion be the cation. This is chromate or chromium, and it has 5 water molecules and 1 chlorine coordinated to it. So that water will be aqua and the chlorines will be chloro. And so I first kind of decide what I have. So my ligands are named here. So I figure out my ligands. I know my chromium is going to be +3, and the name of it's just going to be its elemental name because it's going to be the cation, or the complex ion is a cation. And so then I can add in my prefixes for my ligands and name those. So I have 5 waters, so I have penta-aqua, and I have 1 chloro, so I just put chloro. I don't need to put mono, it's repetitive. And then I can add in the rest of my complex ion, which is the chromium 3. After that, I can follow it with the anion, which is chloride, and I get penta-aqua, chloro, chromium 3, chloride. Whew. All right, now looking at our next one where we have the complex ion is our anion. Before we looked at it as the cation. That means that everything's the same. It just means that the metal ion is going to be named in a funny way, and I should reference a chart. So first I look at my ligands, and I have all the same ligand. They're all these CN, these cyanide atoms. So I'm going to have cyano for my name, for my ligands. Because this is an anion, it's going to be strange. I have to look it up. It's going to be ferrate. I'm still going to put that charge in parentheses with Roman numerals. It's +3. So as an oxidation state of 3. And then I'll put that together for the complex ion. So I have 6 of those cyanide ions. So it'll be hexacyano, ferrate 3. Then I'll put it together with my counter ions, which is the potassium. So it'll be potassium hexacyanoferrate, ferrate 3. Woo, they're mouthfuls. All right, try these problems first. Try naming these, and I'll go over this in the next video.